capital N represents the number of bacteria. Capital T represents the temperature that the food, like of the food. So what is the actual temperature of the food? How cold is the food? So we have the equation here, and then it says temperature is between 2 and 14 degrees Celsius. Now that's Celsius. So remember, 0 degrees Celsius is 32 degrees Fahrenheit, so that would be freezing. So this is 2 degrees Celsius to 14 degrees Celsius. It also says when the food is removed from refrigeration, so we take it out of the refrigerator, the temperature can be given by capital T for temperature of little t for time. So essentially, obviously, the temperature is going to increase. The food is going to get warmer as it sits outside and it's not in the refrigerator. Makes sense. So this formula here, 4t plus 2, that's a linear formula. So essentially, it's increasing by 4 degrees for every hour. Time is in hours. And it has us going from 0 to 3. So for the first question, it says find the composite n of t of t. So a composite function is kind of like substituting. If I look in the middle here, temperature with respect to time is the formula or the equation that we're substituting in. So I have the n, which represents the number of bacteria, and then 4 plus, how about 4t plus 2? That's sloppy. That's better. So if I plug that into the equation for n, wherever I see a t, I should be replacing it with the 4t plus 2. So 20t squared. Well, t squared should be 4t plus 2. And then it says minus 80t. Well, 80t again is 4t plus 2. And then it says plus 500. So that's how I would substitute this into my equation. And then you have to do a little bit of FOILing, because when I'm looking at this, so I replace the t in the number equation, the number of bacteria equation. So there's a quantity squared. That quantity needs FOILed. The 20 stays outside. When you FOIL this, Lucia, what do you get when you FOIL 4t plus 2 squared? What does that become?
16t squared plus 16t plus 4.
Yeah, nice job. And that goes back around parentheses because the 20 outside needs to change everything that we just FOILed together. And then I can distribute the 80 through, so negative 320t minus, what is that, 160, and then plus 500. So now, if I distribute the 20 to every piece that we FOILed, we end up with positive 320t squared, a positive 320t, and then a plus 80. And then the rest of the stuff isn't changing. So it's actually a pretty big problem because there's FOILing. I mean, the initial was a quadratic, a 3-term trinomial quadratic up there. And then finally, the goal is to come up with this final equation, n of t of t. So I see these guys cancel. That leaves me with 320t squared. And then, looks like minus 80, 420. So that would be our final equation for part A with all the simplifying. So it says, what does this function mean? What does it represent? What are we finding here? So what does this 320t squared plus 420 represent based off of this problem? Noah, do you know?
The number of bacteria on the food after however many hours it's been left out.
Yeah, so think about going to a picnic, especially when it was like, 95 degrees this summer. We had a lot, like all of July was hot. So you're leaving the bacteria out, the potato salad, the macaroni salad, the fruit salad, or you're leaving your food out, and it has now bacteria in it because it's getting warmer and it's sitting outside. That's how we would find the number of bacteria in the food. So for part B, it says find the actual number of bacteria in the food after 2 hours. So I would take the same equation and plug in 2 for t. Now I want to know how many bacteria are in my food crawling around after 2 hours. Bridget, how much bacteria is in the food after 2 hours?
1,700.
You think that's a lot? I don't know. To me, it sounds like a lot, but I'm not a biology teacher. Do you think? What do you think?
I have no clue.
No clue. Maybe we should ask Mrs. Ortiz. Does anybody know, is it bacteria or bacteria-I when it's pluralized? I don't know. Again,
It's
I'll ask.
bacteria.
It is bacteria, thank you. So no change in the spelling. It's just bacteria. No pluralization. And then the last question says we want to find the time when the bacteria count reaches 2,000. So I would do exactly the same thing except set my equation equal to 2,000, this equation over here. Because now I want to find time. Oops, 420. And I think this time, is it 2.2, 2.3? 2.22, thanks. And then that's hours. So a little bit more time. We already found the 2 hour mark, so to get up to 2,000, 2.22 hours. Questions? I might have to email Mrs. Ortiz to see if that's a lot of bacteria. But bacteria is good for your body. It's good to introduce some bacteria to it, right? All right, so does anyone have questions on that problem? I'm going to let Thibaut in, see if he's still here. He is still here. All right, so today we're going to find inverse functions, as I said. Not only are we going to find them, but we're also going to verify that two equations that we would be given are inverses of each other. If you could get out your calculator, we're going to look at the calculator as well, because I want to look at it algebraically, but also graphically, so we can kind of do both parts. Please remember to submit that homework assignment. If you haven't done so already, submit it with those corrections on it as well. Yeah, of course, yeah, just scan the little code over there. Does anybody need paper to take notes? So, inverse functions. That's what we're looking at, the last concept. This whole chapter was functions and their graphs. So what can you do with the function? What can you do with their graphs? What does it mean for something to have an inverse? Or what would be another word you could use for inverse? Tyler, what do you think? Opposite, that's a great word. So, Tyler, if we had 2 times x, the opposite of 2 times x would be? Yeah, or the other way around, x divided by 2, if x was my variable. So, opposite operations, multiplication and division, are inverse operations. Adding and subtracting are inverse operations as well. So, we're going to find an inverse function. And the way you find an inverse function, so we're going to first talk about how do you find it. It's found by switching or interchanging the x and the y variables, because x and y are opposites, they're inverses. So found by interchanging. If you'd rather say switching, you can say switching, whichever term you like better. The x and the y variable. And then solving that new equation for y. It's a good song. So I'm going to show you a basic example so that we can kind of look at that notice part. I'm going to give you a function of just a set of pairs, ordered pairs. So we're going to look at a function of ordered pairs, and I'm going to call it f of x. Remember, a function is when each x has one y. So inverse functions, it has to be a function for it to have an inverse. That's like the first stipulation. If it isn't a function, then it's not going to have an inverse. So my inverse function here, I'm just going to come up with a couple of points. So 3, 2, -1, 5, about 7, -6. They're really rocking out there. What kind of vehicle is it, Lucia? Oh, of course, FedEx. Those people drive like crazy in my neighborhood. I think they have to like drop off so many packages in probably, I don't know, 5 minutes, but they like fly. And somebody, it might be FedEx, they only make left turns or right turns. Maybe they only make right turns because you don't have to stop making a right turn. So they'll go around my neighborhood only making right turns, which still seems like it defeats the purpose because then they have to like back circle. I don't know. I'm glad I'm not a delivery man or woman. I could be either. All right, so that's my function. If I want to find the inverse function, notice this little notation here with the -1. That's our inverse notation. So if we have an inverse, we have special notation to show that it's an inverse. Just like if we have a function, we use f of x. So an inverse gets that little extra -1. So if our function is 3, 2, -1, 5, 7, -6, that set of ordered pairs, what would the inverse be? Tyler, what do you think? You're making it harder than it is. Found by interchanging x and y. So what would you do with x and y if you're interchanging them? Just switch them. Yeah, so my inverse function, if you just switch those, we would have 2, 3. Now I have an inverse. I switched x and y. 5, -1, and -6, 7. So literally, an inverse function can be found just that simple by taking a set of points, switching x and y. That's how you find an inverse. So the part right here says the domain of f is equal to the range of the inverse. So if we talk about that, the domain of f, here's the domain. Domain, remember, is the x. Has become the range of the inverse. Well, now if I look, it is now the range. Because what was x is now y in my inverse function. X is domain, range is y. So they should switch. So if it was the domain, it's now the range. And it works the same way. If it was the range, now it's become the domain of the inverse. So saying I switch x and y also means we're switching the domain and the range. So it kind of makes sense that it happens that way. Questions? So here's this big important definition because I gave you the way to find an inverse function, but inverse functions are usually a pair because I have its function and the inverse, and they kind of combine together or grouped together. So this definition, I'd like put a star next to it because you're going to see this definition in the very near future, or you might be asked to explain this definition in the very near future. Is that a hint? Yeah, a little bit. So two functions are inverses of each other. And again, inverses are grouped as a pair. So one function and another are kind of considered inverses of each other. If, and here's the important part, which is why last week we did these on Thursday and Friday, f of g of x equals x. So when I take the composite functions, when I take those two functions and combine them together, if those two functions combined together equals x, and if I go the other way, g of f of x also equals x, then the two functions are considered inverses. So again, one function and a second function. When I look at the two of them, I'm not finding an inverse. I'm saying they're inverses of each other if f of g of x equals x and g of f of x equals x. The part underneath is just saying it in the inverse function notation, showing you that you have the inverse and the function combined together. The key thing is that they must equal x for them to be inverses. And we're going to show you algebraically and also graphically what that should look like. So this is like a proof as to functions, two functions being inverses of each other. And I know you don't like that word proof from geometry. So I changed it to verify because people like verify better than prove. I don't know why. So example 1 that we're going to do underneath, we're going to try and use this definition to show that functions are inverses. Verify that the two functions that are given, so we're going to use these given functions, are inverses of each other. We're going to look at it algebraically and graphically. So I'd like you to see if you can kind of solve these algebraically. All I have to do is show that f of g of x equals x. And then I have to flip it and show that g of f of x equals x. If I can show both of those are equal to x, then I've verified or proved that the functions are inverses of each other. So we should have things canceling because that's what happens with inverses. If I add 3 and then subtract 3, they cancel and give you 0. So looking at the first one, I'm plugging the g function, which is 3 minus x over 4, into f. Remember, the f function is 3 minus 4 and then times x. So I'm taking this 3 minus x over 4. So we're plugging that in. When you plug that in, instead of distributing the negative 4 through, which you could, what's something else that happens with that negative 4 when it's sitting outside? And then I have this 4 that's on the bottom. What happens to that? So I'm multiplying by negative 4 outside of the parentheses, but inside the parentheses, we're dividing by 4. Lucia, do you know what happens with those? Yeah, they could just cancel out. So we don't have to distribute 4 through. Our goal is to get things to cancel. Let's just cancel them out. Dividing, multiplying, opposite operations. There's a negative sign that's left, so make sure that we distribute that negative through. So we end up with a 3 minus 3 plus x. Maya, what happens with the 3 minus 3 plus x?
Cancel out.
And they just equal? X. Woohoo! That was part of what we were trying to show. Now I've showed that the one side is equal to x. I just have to do the same thing with the other side. All right, so let's look at this other part here. We're taking the f function and plugging it into g. So g says 3 minus x over 4. Again, just be careful when you're plugging that x in. Place it in parentheses so that you know you're subtracting that whole quantity for x. So we're subtracting 3 minus 4x. So if I distribute the negative through, this time I do want to distribute the negative through because it's on the top of that numerator. We end up with 3 minus 3 plus 4x divided by 4. And if I look at this here, 3 minus 3 cancels. And then my 4x divided by 4 is just
X.
Just x. So verifying is a fancy way of saying prove. I've shown that these two functions are inverses of each other by using composite functions. By definition, if they both simplify just to be x, then they're inverses of each other. So that says that 3 minus 4x is the inverse of 3 minus x over 4. And if you look at it, it makes sense because I have like a negative 4 as a slope, and now this slope is a negative 1/4. So it does kind of make sense that that works out like that. Questions? So now I'd like you to take your calculator out because I said we were going to do this two ways. This is the algebra proof. I've shown now that they break down to be x. If you can go in your calculator and plug in both of those equations. When you plug into a calculator and there's a fraction, make sure that the g of x fraction has parentheses around that 3 minus x. So please make sure when you plug the numerator in, the numerator 3 minus x is in parentheses. So when you hit graph, the blue line that comes up here was my f equation. So the blue line is my f function, the 3 minus 4x. My line is black, the second line, which isn't as steep as the first because its slope was negative 1/4. That's the black line. So we're trying to figure out, why do these look like inverses graphically? What's special about them graphically that would show that they are inverses of each other? So what would be special about them? Lucy, you notice anything special?
Not about the lines specifically, but their points are X and Y coordinates are switched.
Ooh, that's a really good thing. So how'd you know that? That's what makes it an inverse function. So if we look at the table of values, maybe we could try and see that we have ordered pairs that might switch. So we should have a point at for one that matches with the other. I don't know if I can find any that work like that. So here we go. So here's 7 and negative 1. So we could kind of then flip that and see if that would work. Oh, right there, negative 1 and 7. So yeah, they definitely flip. So I had a point at 7, negative 1. Now I have a point at negative 1, 7. So that's good because that's what has to happen. I also see that they intersect right here. They're intersecting at that point there. I'm going to go back to y equals, and in my third spot, I'm going to place that x because algebraically they simplified to be x. So I'm just going to throw an x in there. I mean, that x might mean something. And if you hit graph, that y equals x line, notice that it intersects exactly at the point where the other two lines are also intersecting. And that's because the two lines are reflections over y equals x. So my steeper line is in blue. It is reflecting diagonally, which is weird to think for something to reflect diagonally, but it's reflecting diagonally over the line y equals x. That's why they're inverses graphically of each other. So I'm going to go back to my screen here. It's a little slow. There it comes. So what is special graphically about two functions? Well, graphically, they're going to be reflections over the line y equals x. So that x means something in the equations. In the graph, it means that they should reflect over that line. So we talked about reflecting over the x-axis. We talked about reflecting over the y-axis. Well, if lines or graphs reflect over y equals x, then they're inverses of each other. Questions? So if you look at the second one, we're not going to do this algebraically, but I want you to keep that calculator out. And let's see if we can plug this in the calculator just to show you what it looks like to have a different function graphically. So we're not going to do this one algebraically. Let's go in the calculator and see if we can plug these in. So 2x cubed minus 1. We're going to take that and plug that into the first. I want you to kind of be able to see what happens. I'm going to keep that x in my calculator as well. Forgive us that it was plus 1 over 2. So we have 2x cubed plus, or minus 1? What's that plus? No, it was minus 1. 2x cubed minus 1. And then the second one is the cube root in parentheses x plus 1. And then over 2. And then I also kept that x in there. I feel like I'm missing half of my graph. I don't know why my black line for some reason is not graphing the bottom part. I don't know why. But this line here should come down and kind of curve over. I think yours probably does. I don't know why mine isn't. Does yours? Yeah. Mine seems to want it to stop at the x-axis. I'm not sure why it's stopping. But my black line should continue to go down and cross. And it should really do the opposite or the inverse of the blue line. I don't know why it's not showing up. But you can kind of see, get a better idea, at least if you look at your graph, you get that more like reflection over that y equals x line. It looks like more of a reflection with these two functions, the cube root and the cubic functions. Does anyone have questions? So the other thing that we're going to talk about today is the fact that graphs, not all of them have inverses. So this is an example of one that definitely is an inverse because it's a reflection of the line y equals x. But we're going to see maybe why some would not have inverses. So if you go to the next page, the next slide, I'm going to skip the graphing part, but just kind of highlight graphs of f of x and the inverse are reflections of each other over the line y equals x. So just as like highlighting, reminding you. So algebraically, f of g of x must equal x, g of f of x must equal x. Graphically, the two functions are going to reflect over the line y equals x. So the last thing we're going to talk about would be why does a function have an inverse, but another function may not? So not every function has an inverse. In order for a function to have an inverse, the function must pass the horizontal line test. So I told you about a vertical line test in section 1-2. Vertical line test, each x has to have one y. We drew vertical lines, and as long as the vertical line crossed through the graph once, it passes the horizontal line test, or the vertical line test. Well, the horizontal line test is essentially the same thing, except now we're drawing horizontal lines. So for a function to be 1-to-1, if it passes the horizontal line test, a function is 1-to-1. And what that means is it's a two-part thing. The first part, each x has exactly one y. That's the function part. The second part, each y has exactly one x. That's the horizontal part. So it has to be a function, each x must have one y. But the horizontal line test then shows me that each y has exactly one x. If that happens, then my graph or my function has an inverse. So it has to pass the vertical line test to be a function, and then it has to pass the horizontal line test for it to have an inverse. If it does, we call the function 1-to-1, because 1x for 1y and 1y for 1x. So we call it 1-to-1. So down below, we're just going to look at these graphs and see if this function is 1-to-1, which means it has to pass the horizontal line test if it's 1-to-1. If it does pass that, then the function has an inverse. So Noah, if you look at the first one, we have x cubed plus 1. What would that graph look like, x cubed plus 1?
It would look like
Yeah, perfect. Love your air drawing. So increases from the left, it scoots up, it continues to go up, and it crosses the y-axis at the value of 1. That's what that plus 1 does. So that's my graph. Noah, is this a function? Let's start off with that. Is y equals to x cubed plus 1 a function?
Yeah.
Would it be 1-to-1? Would it pass the horizontal line test? Yeah, because I could draw horizontal lines. It only crosses through my graph once. So is this function 1-to-1? Yes, it is 1-to-1. passes the horizontal line test. Now it's 1 to 1. Each x has one y, each y has one x. So if it is 1 to 1, does it have an inverse? Yes. So I can say yes to both of those. As soon as you say yes, it's 1 to 1, then yes, it has an inverse. On your homework tonight, it asked you to show this algebraically and graphically. I only want you to show it graphically. So draw me a little graph. Yes, it passes the horizontal line test, so it's 1 to 1 and it has an inverse. Don't worry about the algebra part. And I have that in the agenda and in the assignment itself as well. So the second one, we have the square root of x. What does the square root of x look like? Emma, do you remember what the square root of x looks like?
It's at the origin and it kind of like goes in.
Perfect, yeah. So at the origin, she said, and then it kind of like hooks to the positive values. So it's the positive values at the origin. Emma, is this a function?
Yes.
Yeah, it better be because I use g of x, so it better be a function. Is that function 1 to 1, Emma? Does it pass the horizontal line test? Yeah. This does keep, like it keeps increasing. It might be a gradual increase, but it's never going to have like flatten out horizontally. So yes, it's 1 to 1. And then it also has an inverse function that we can find. So I left part C blank because I want you to think of a function that would not have an inverse. That's why I left it blank. What function would not have an inverse? So think, what graph would not cross the horizontal line test? Bridget, do you know? Sorry, I thought you were raising your hand. I got all excited. Maya.
Like y equals 0 or y equals any of.
Yeah, any horizontal line. So y equals 0, y equals 5, y equals 10. Horizontal line, not going to work. What else wouldn't have an inverse? Noah.
Parabola.
Ooh, that's one of my favorite graphs. It's sad that it doesn't have an inverse. Parabola is a U. It's not going to have an inverse. What else wouldn't have an inverse? Piecewise functions, yeah, because they're kind of crazy. They're not going to be passing the horizontal line test. There's one more. It doesn't make a U, but it makes another letter. You see it? Yeah, absolute value. That's not going to have an inverse. So there's actually a lot of functions that don't have inverses. So it has to be pretty specific for it to have an inverse. So we're going to see if we can actually find the inverse. If I have x cubed plus 1, how can I get its inverse? Because the problem that we looked at before, and you don't have to flip pages. Here it goes. The problem that we started with, it gave us two functions and it said prove that these are inverses. Well, now we actually want to find the inverse, and that's what we're going to do, the last thing we're going to look at. So in your packet, if you just scroll down to the next page, if you say yes, a function has an inverse, then you'll be asked to actually find the inverse function. So if I look at example A, this is the one that we just did, and we said yes, this has an inverse. It passes the horizontal line test. The directions are really easy. Yes, it's 4 steps, but it's an easy 4 steps. So if an inverse exists, if you say yes, it has one. The first step, replace f of x with y. Well, that's really easy. Without even rewriting it, I'm just going to make it a y. Interchange x and y. Remember, that's how you find an inverse. So switch them. Now it's x equals y cubed plus 1. So that step's easy. Step 3, solve for y. Remember, my equation needs to be in y equals. I'm trying to find the inverse, so I have to get it back in y equals form. So I would take the 1 to the other side. And then Maya, how do you get rid of y cubed?
Cube root.
Cube root, yeah. So take that cube root. So now I have y equals the cube root of x minus 1. The last step, don't forget about the last step. I did all this work, I have this new equation, but that new equation represents the inverse of its initial function. So make sure that you say that this is the inverse that you found. So the inverse is equal to the cube root of x minus 1. And it makes sense because we started with a plus 1. Well, now its opposite is minus 1. It started with x cubed. Well, the x cubed, the opposite must be the cube root of x. So the two functions, like, they look like they're opposites as well. Any questions? I bet you could quickly do letter B. See if you could try and find the inverse of that as well. So your homework, I think there are, I'm going to say it's 9 problems. A couple of them are going to be, yes, it's an inverse, and then find it. I think 2 of them are just verifying the f of g of x, the g of f of x. And then there's also a problem or 2 where you're just looking at a graph and saying it's 1-to-1, or it's not 1-to-1. But again, this is a square root graph, so I know a square root graph has to have an inverse. So tomorrow we're going to look at functions that don't have inverses and see, like, how can I force them to have an inverse? What could I do to the problem to make it have an inverse? So I'm just solving this problem here, trying to get y by itself. I had a square root, so I have to square both sides. I need to add the 3 to the other side. And then I need to divide everything by 2. Make sure that you're writing the inverse. If it's a g function, then use g negative 1. X squared plus 3, and then divide it by 2. Does anyone have questions? Anyone at home have questions about the concepts we talked about today?
Nope.
How did it sound today? It doesn't sound good. All right, so have a great day. I guess they're not going to let you out early today. I don't know.